Here are a few more results concerning the exponential distribution. First result is the self-reproducing property. There are three assumptions that go into this. First of all, if T1 through Tn are independent, and second of all, if T sub I is exponential lambda I for I equals 1 to n, and you'll notice that the lambda sub i's do not have to be identical here. You can have different failure rates for each of the T sub i's. And the third assumption is there's a new random variable T, which is the minimum of T1 through Tn. So the conclusion here is the random variable T, which is the minimum, is exponentially distributed, and its rate parameter is the sum of the individual failure rates for T1 through Tn. Another way of saying this is the minimum of n mutually independent exponential random lifetimes, possibly with different failure rates, also has the exponential distribution, and its failure rate is the sum of the failure rates for the individual exponential random variables. Two applications. The first one is if you have a series system of independent components and they have exponential lifetimes. So here is a series system of n components, and the first component has failure rate lambda 1, second component failure rate lambda 2. The nth component has failure rate lambda n. Then in that case, the system time to failure is exponential, and its rate is the sum of the component failure rates. As another application, if you have several independent exponentially distributed causes of failure, then a competing risks model for the lifetime of the item is appropriate. So in a sense here, rather than having individual components, you just have one item and the various risks that can cause failure are competing. An example of that might be a cell phone, where the cell phone can be dropped, or the cell phone can have electrical problems that go out, or there might be something mechanical like a switch that can cause failure, and those three risks are competing for the lifetime of that cell phone. Here's a proof of the self-reproducing property. The survivor function of T is S of T is the probability that T is less than or equal to T. That comes simply from the definition of the survivor function. And that T can be replaced by the minimum. That's simply the definition of T as the minimum of T1 through Tn. Now this next step here, if I were to draw a timeline moving to the right, and let's say this is time 0 right here, if you were to let this point right here arbitrarily be T, well, if the minimum of all those variables is greater than or equal to T, then what that means is, let's say the minimum falls right here, that means that all of them have to be greater than or equal to T. So not only the minimum, but the second smallest, third smallest, etc., all of them are greater than or equal to T. So you can think of that step there as equivalent events. This can be broken into the product of the probabilities by independence. So that takes you to this step. Each one of those can be recognized as a survivor function. So what you do then is you say, what is the survivor function of an exponential random variable? And that survivor function will be e to the minus lambda 1t, e to the minus lambda 2t, etc. And finally, this last step here is just a little bit of algebra, which says like base, add exponents, and you get this quantity. Now notice the form of this thing. This is a survivor function of capital T, and it's e to the minus, and here is a constant in parentheses times t, and what that tells you is you are again exponentially distributed, and the parameter in the exponential distribution is the sum of the lambda i's. Property 7 goes like this. If T1 through Tn are mutually independent and identically distributed exponential lambda random variables, then 2 lambda times the sum of the Ti is chi-squared 2n degrees of freedom. The setting where this might come up is in something called life testing. Let's assume that we've got 4 light bulbs that we're going to place on test, and remember, these light bulbs are all of the same wattage and the same brand. So these might be 60-watt General Electric light bulbs. Let's just say the first one fails here, second one fails here, next one fails here, finally the last one fails right here. Now when we get to chapter 7, we're going to find out ways of estimating lambda hat, but the application here is to find a confidence interval for lambda, which will give us a clue as to how much precision we have for lambda hat. So with probability 1 minus alpha, since this quantity right here is chi-squared 2n, we can take that quantity and trap it between the alpha over 2 fractile of the chi-squared distribution with 2n degrees of freedom and the 1 minus alpha over 2 fractile of the chi-squared distribution with 2n degrees of freedom. Now notice that in this particular setting we are using right-hand tail probabilities here. So that's why the fractile subscript may not match what we have here. And that's this note right here. When we rearrange this and try to trap lambda in the middle of the inequality, well, we're dividing all 3 of those by twice the sum of the TI's, and that is always a positive quantity, so you wind up with this expression right here, and that is an exact confidence interval for alpha. And in fact, it is a 100 times 1 minus alpha percent confidence interval for lambda. We'll use that quite a bit when we get to chapter 8. Another application that comes up when you have T1 to Tn exponential lambda random variables also applies in the life testing setting. This time what we're going to do is define what are known as order statistics. This is simply that raw data T1 through Tn, but this time sorted from smallest to largest. Those are known as order statistics. And then we're going to define a G sub I. And G sub I is going to be the gap between various failures. So this is going to be T sub I minus T sub I minus 1 for I equals 1 to n. And then if we arbitrarily set a 0th order statistic to be 0, then the following 2 results spill out. The first one says that the probability that G sub I is greater than or equal to t is e to the minus n minus I plus 1 lambda t. You'll recognize this left-hand side as a survivor function, and you'll notice that this right-hand side is e raised to the negative constant times t. Well, says that you have exponentially distributed gaps. Finally, the second piece of the result here says these gaps are mutually independent random variables. Let's go down to the bottom here. If you place 4 items on a life test, and remember those are all identical light bulbs, for example, here is when the initial failure occurs. That's T1, the first order statistic. Here's when the next failure occurs, the third, and then the final failure of the 4 occurs right there. The gap statistics are the times between these failures, and those are G1, G2, G3, and G4. This can be interpreted as a life test of n items having exponential lambda failure times. We don't replace the items when they fail, and the ith item fails at time t sub I. That's the ith failure, and the gap is the distance between the 2 failures. Turns out these G sub i's are independent, and that is from the B result. And in addition, they're exponentially distributed, and that's from the A result. Now notice they have different exponential distributions because the parameter depends on I. A little bit of intuition from this picture right here. The test starts at time 0 and all 4 light bulbs are on the test. When that initial failure occurs, there are 3 light bulbs that are still burning. But by the memoryless property, each of those 3 light bulbs that are still burning have the memoryless property, so they have an exponential time to failure. And the same is true when the second failure occurs and when the third failure occurs. Notice that G1 is the minimum of 4 exponential random variables, but G2 is the minimum of 3 exponential random variables, etc. Property 9 is about order statistics. Let's draw that same picture again here. We have, let's just say, 4 bulbs on test. Let's say bulb 1 fails here. Bulb 4 fails here. But this time, when bulb number 4 fails, that bulbs 3 and 4 are still burning. In this case, we have n equals 4 items on test, and let's say we terminate that test when the second failure occurs. So bulb 1 was the first to fail, bulb 4 was the second to fail. We stop the test, which means bulbs 2 and 3, their lifetimes are right-censored. So here is a theorem that you can use in that particular setting. T1 through Tn, and that's our T1 through T4 in this case, those are IID, exponential lambda random variables. So if these are light bulb lifetimes, then all of them are identical light bulbs, same brand, same wattage. And if T sub R is the time of the rth failure, and that is the rth order statistic, then the expected time to complete the test is given by this summation, and the variance of the time to complete the test is given by this summation for r equals 1 to n. This is useful in determining the expected time to complete a life test that is discontinued after r of the n items on test fail. And in our particular example right here, we have 4 items on test, and we conclude the test when the second one fails.